the star that outshines the light of entire galaxies. In the depths of space, 13 billion light-years from Earth, something burns with the fury of a trillion suns. It is not a galaxy. It is not a cluster of stars. It is a single point of light, one star, that blazes brighter than the combined luminosity of every star in the Milky Way. Its name is R136a1, and it should not exist. When astronomers first detected the celestial monster through the Hubble Space Telescope, they questioned their instruments. No star, according to everything we understand about stellar physics, should possess such impossible mass, such devastating luminosity. Yet there it burns, defying the very laws that govern how matter behaves under gravity's crushing embrace. This star contains the mass of 250 suns compressed into a sphere that could fit within our solar system, radiating energy so violently that it strips atoms apart across distances that span light years. But R136a1 is not alone. Deep within the Tarantula Nebula, in the satellite galaxy we call the Large Magellanic Cloud, it anchors a cluster of similar impossibilities, each one a hypergiant that challenges our understanding of how the universe builds its most extreme structures. These are not just stars. They are cosmic furnaces so intense they may rewrite the periodic table, forging elements that exist nowhere else, burning through millions of years of nuclear fuel in mere millennia. What forces could birth such monsters? Why do they exist in apparent violation of the stellar mass limit that should prevent their formation? And what does their existence reveal about the hidden violence that shapes galaxies, time, and the very fabric of space-time itself? The story begins not with the star itself, but with a nebula that has haunted astronomers for centuries. Long before humans had names for the constellations, before they understood that stars were distant suns, the Tarantula Nebula cast its ghostly light across the southern sky. To the naked eye, it appeared as nothing more than a faint smudge of luminescence, a cosmic cloud drifting through the void like smoke from some celestial fire. In 1751, French astronomer Nicolas Louis de Lacaille became the first to catalogue this mysterious object during his pioneering survey of the southern heavens from the Cape of Good Hope. Through his modest telescope, the nebula revealed itself as a spider-like structure of glowing gas, its tendrils reaching across space like the legs of some cosmic arachnid. He designated it NGC 2070, but the name that would endure was far more evocative: the Tarantula Nebula, a stellar nursery of unimaginable violence and beauty. For more than 2 centuries, the tarantula remained a beautiful but unremarkable feature of the Large Magellanic Cloud, our neighboring galaxy. Astronomers understood it as a region where new stars were born, where gravitational collapse transformed cold gas into nuclear furnaces. It was similar to countless other star-forming regions scattered throughout the cosmos, distinguished only by its size and the ethereal beauty of its glowing hydrogen clouds. The revolution began on April 24, 1990, when Space Shuttle Discovery carried the Hubble Space Telescope beyond Earth's atmosphere. As Hubble's unprecedented resolution pierced through the nebula's glowing veils, astronomers at the Space Telescope Science Institute began to see the Tarantula Nebula as no human ever had before. Individual stars emerged from the cosmic fog like lights being switched on in a darkened city. At the nebula's heart lay a dense cluster of brilliant blue-white stars, designated R136, that seemed to burn with impossible intensity. Dr. Anthony Moffat of the University of Montreal was among the first to realize they were witnessing something that challenged conventional understanding. His spectroscopic analysis revealed stars emitting ultraviolet radiation at levels that exceeded any known stellar classification. These were not ordinary massive stars. They were objects operating at the very edge of physical possibility. The breakthrough came through painstaking observation and analysis. As Hubble continued its surveys through the 1990s and early 2000s, astronomers began measuring the properties of individual stars within the R136 cluster. They discovered surface temperatures reaching 50,000 Kelvin, nearly 10 times hotter than the Sun. The star's spectra revealed elements ionized to degrees that should be impossible in normal stellar atmospheres. Most disturbing of all, calculations based on the star's luminosity and temperature suggested masses that violated fundamental principles of stellar physics. In 2010, Dr. Paul Crowther of the University of Sheffield led the most comprehensive study yet undertaken of the R136 cluster. Using both the Hubble Space Telescope and the Very Large Telescope in Chile's Atacama Desert, his international team focused on the cluster's central star, R136A1. Through months of careful spectroscopic measurement and sophisticated stellar modeling, they arrived at a conclusion that sent shockwaves through the astronomical community. R136A1 contained approximately 265 solar masses, nearly double the theoretical limit for stellar formation. It was a discovery that would force scientists to question everything they thought they understood about how the universe builds its most extreme structures. The star that emerged from their data was not merely massive, it was impossible. And yet, there it burned, a cosmic furnace that challenged the very foundations of stellar physics. The implications were staggering. If R136A1 existed, then the universe operated according to principles far more complex and violent than previously imagined. It suggested that somewhere in the depths of space, forces were at work that could overcome the fundamental limits that should govern stellar formation. The discovery opened a door to questions that would reshape our understanding of how matter behaves under the most extreme conditions in the cosmos. The existence of R136A1 violated one of astronomy's most fundamental and sacred principles, a limit established nearly a century earlier by one of the greatest minds in astrophysics, Sir Arthur Stanley Eddington, the British physicist who had confirmed Einstein's theory of general relativity during the famous 1919 solar eclipse, had discovered something profound about the nature of stars themselves. In the 1920s, through elegant mathematical analysis, Eddington revealed that every star engaged in a cosmic battle between two opposing forces. On one side stood gravity, the relentless inward pull that seeks to collapse all matter into an infinitely dense point. On the other side blazed radiation pressure, the outward force generated by nuclear fusion in the star's core, as photons struggled to escape the stellar interior. Eddington calculated that as a star's mass increased, this battle became increasingly violent. The more massive the star, the more furious its nuclear burning, the greater the outward pressure of radiation. Eddington's mathematical poetry revealed a critical threshold, approximately 120 to 150 solar masses, beyond which radiation pressure would inevitably triumph over gravity. A star attempting to exceed this limit would literally blow itself apart, its outer layers stripped away by the fury of its own nuclear fire. This became known as the Eddington limit, and for nearly a century, it stood as an immutable law of stellar physics. Every star ever observed had respected this cosmic speed limit. From the smallest red dwarfs to the most massive blue supergiants, all stellar objects fell comfortably within Eddington's theoretical boundaries. The universe appeared to follow strict rules about how massive its stellar children could become, rules written in the fundamental constants of physics itself. R136A1 shattered these rules with casual indifference. At 265 solar masses, it exceeded the Eddington limit by nearly double. According to everything astronomers understood about stellar physics, R136A1 should have exploded the moment it attempted to ignite nuclear fusion in its core. Its radiation pressure should have overwhelmed gravity's grip, dispersing its mass across light years of space in a catastrophic stellar explosion. Yet there it burned, stable and serene, its spectrum showing no signs of the violent instability that theory demanded. The implications struck at the very heart of astrophysics. If the Eddington limit could be violated, then fundamental assumptions about stellar evolution, galaxy formation, and the distribution of matter throughout the cosmos required complete reevaluation. The limit wasn't merely a theoretical curiosity. It underpinned calculations about everything from the chemical evolution of galaxies to the formation of the first stars in the early universe. Scientists found themselves confronting an uncomfortable possibility. Either their understanding of stellar physics was fundamentally incomplete, or R136A1 represented something entirely unprecedented, a type of stellar object operating under physical principles that had never been observed or theorized. The discovery forced astronomers to question not just what they knew about stars, but what they thought was possible in a universe governed by the laws of physics. Some researchers initially questioned the observations themselves. Could R136A1 actually be multiple stars so close together that they appeared as one? Could there be systematic errors in the spectroscopic analysis that led to incorrect mass calculations? But as independent observations confirmed the initial findings, the scientific community was forced to accept a troubling reality. The universe had produced something that shouldn't exist, and it was burning peacefully in defiance of a century of theoretical physics. R136A1 wasn't just an anomaly. It was a cosmic riddle that challenged the very foundations of how scientists understood the relationship between matter, energy, and gravity in the most extreme environments the universe could create. The star's existence raised profound questions that extended far beyond stellar physics. If nature could violate the Eddington limit, what other theoretical boundaries might be illusions? What other impossible objects might exist in the depths of space, waiting to shatter human understanding once again? As news of R136A1's impossible existence rippled through observatories around the world, telescopes, both terrestrial and orbital, turned toward the Tarantula Nebula with unprecedented focus. The European Southern Observatory's Very Large Telescope in Chile's Atacama Desert began systematic observations using advanced interferometry techniques that could resolve details smaller than the apparent size of a coin on the moon. The Spitzer Space Telescope contributed its infrared vision, peering through cosmic dust to reveal the hidden thermal signatures of the Hypergiant cluster. High above Earth's atmosphere, the Chandra X-ray Observatory detected the violent high-energy emissions that betrayed the extreme physics occurring within R136A1's stellar atmosphere. Each new wavelength of observation revealed layers of mystery that deepened rather than resolved the central paradox. Spectroscopic analysis confirmed that R136A1's surface blazed at temperatures reaching 53,000 Kelvin, so hot that its blue-white light contained more energy in the ultraviolet spectrum than in all visible wavelengths combined. To stand on a hypothetical planet orbiting at Earth's distance from such a star would mean instant vaporization, as ultraviolet radiation intense enough to ionize atoms stripped away the very building blocks of matter. But temperature was only the beginning of R136A1's impossible characteristics. Measurements of its luminosity revealed that this single star radiated 8.7 million times more energy per second than our Sun. To comprehend such numbers requires abandoning human scales of reference entirely. R136A1 alone outshines entire dwarf galaxies containing millions of ordinary stars. Its light, traveling at 300 million meters per second, would require nearly 4 years to reach Earth from the star's surface. Yet that surface burns so brilliantly that it would appear brighter than Venus in our sky, despite being located in another galaxy entirely. The mystery deepened as astronomers realized that R136A1 was not unique within its stellar nursery. Systematic surveys of the R136 cluster revealed dozens of other hypergiants, each possessing masses that challenged theoretical limits. R136A2 contained 195 solar masses. R136A3 weighed in at 180 solar masses. The cluster harbored at least 40 stars exceeding 100 solar masses, a population of impossible objects that transformed the Tarantula Nebula from a typical star-forming region into something resembling a cosmic laboratory for extreme physics. Perhaps most disturbing was the discovery of these stars' youth. Stellar evolution models, refined through decades of observation and theory, indicated that the hypergiants were mere infants, only 1 to 2 million years old. In cosmic terms, they had been born yesterday. Yet somehow, in this impossibly short span of time, they had accumulated masses that should take tens of millions of years to gather through conventional stellar formation processes. Our Sun, by comparison, required approximately 50 million years to accumulate its single solar mass during its formation 4.6 billion years ago. Further investigation revealed another layer of the mystery that challenged fundamental assumptions about stellar formation itself. Chemical analysis of the hypergiant spectra showed that they had formed from remarkably pristine gas clouds, material containing minimal amounts of elements heavier than hydrogen and helium. This suggested conditions similar to those in the very early universe, when the first generation of stars began to shine in the cosmic dark ages following the Big Bang. Yet early universe physics should have made the formation of such massive stars even more difficult, not easier. Without heavy elements to facilitate cooling during gravitational collapse, gas clouds in the primordial universe should have fragmented into smaller pieces, creating many modest stars rather than a few giants. The existence of hypergiants formed from pristine material violated theoretical models of stellar formation in low metallicity environments. As months of observation accumulated, astronomers discovered that the hypergiants exhibited another anomalous characteristic. Their stellar winds were stripping away mass at rates that defied conventional understanding. R136A1 was losing material equivalent to Earth's entire mass every few thousand years, accelerated to velocities of 2,600 kilometers per second by radiation pressure from the star's nuclear furnace. These winds were so intense they created shock waves in the surrounding nebular gas, generating cavities of superheated plasma that glowed in X-ray wavelengths. The mass loss presented yet another paradox. If R136A1 was shedding material so rapidly, how had it maintained its extreme mass long enough for human observers to discover it? Stellar evolution calculations suggested that hypergiants should consume their nuclear fuel and explode as supernovae within just a few million years, yet the spectroscopic evidence indicated these stars had already burned steadily for 1 to 2 million years, while somehow maintaining their extraordinary masses. Each observation raised more questions than it answered, transforming R136A1 from a simple anomaly into a cosmic puzzle that challenged multiple branches of astrophysics simultaneously. As research into the hypergiant population of RR136 progressed through the following decade, scientists uncovered evidence that elevated the mystery from merely puzzling to potentially paradigm-shattering. High-resolution observations revealed that the mass loss from these stellar monsters was not simply dispersing into space as theoretical models predicted. Instead, something far more complex and unprecedented was occurring within the dense stellar environment of the cluster itself. Computer simulations run on supercomputers at institutions around the world began to reveal the chaotic gravitational ballet occurring within R136. The cluster contained more than 100,000 stars packed into a region merely 20 light-years across, a stellar density thousands of times greater than the neighborhood surrounding our Sun. In this cosmic metropolis, gravitational interactions between stars created a dynamic environment where stellar orbits shifted constantly, where close encounters could alter stellar evolution in ways never before observed. Within this gravitational maelstrom, astronomers discovered what they termed stellar recycling, a phenomenon that challenged fundamental assumptions about how matter behaves in dense stellar environments. As hypergiants shed their outer layers through powerful stellar winds, the ejected material didn't escape into interstellar space as expected. Instead, the complex gravitational field of the cluster trapped much of this gas, redistributing it through gravitational interactions and stellar collisions. Some of this recycled material appeared to be accreted by other cluster members, potentially allowing certain stars to continue growing beyond their theoretical formation limits. The discovery suggested that R136A1 and its companions might not represent stars that had formed with impossible masses, but rather objects that had accumulated additional material through processes that operated only in the most extreme stellar environments. Yet this explanation created new problems even as it attempted to resolve old ones. Stellar merger events, while capable of creating temporarily massive objects, should produce unstable configurations that would quickly shed excess mass or explode. The hypergiants of R136 showed no signs of such instability. Their spectra indicated stable stellar structures burning hydrogen in their cores through conventional nuclear processes, despite possessing masses that should make such stability impossible. Even more troubling was the discovery of evolutionary tracks that made no sense within conventional stellar theory. Detailed spectroscopic monitoring revealed that some hypergiants appeared to be growing more massive over time, rather than losing mass through stellar evolution. R136A1 itself showed spectral characteristics suggesting it had gained rather than lost mass during the years of observation, a phenomenon that violated every model of stellar evolution developed over the past century. The implications extended far beyond the R136 cluster itself. If hypergiants could exist in the current universe, where gas densities were relatively low and heavy elements relatively abundant, they must have been even more common in the early universe. The first generation of stars, population 3 objects that formed from the pristine hydrogen and helium left over from the Big Bang, might have been far more massive than previously imagined. This realization sent shockwaves through cosmology. Models of early galaxy formation, chemical evolution, and the reionization of the universe all depended on assumptions about the typical masses of the first stars. If those first stellar objects were hypergiants similar to R136A1, they would have lived faster, died more violently, and enriched the early universe with heavy elements at rates that could fundamentally alter the timeline of cosmic evolution. The mystery deepened further as astronomers realized that hypergiants might represent only the visible tip of an even more extreme phenomenon. Theoretical calculations suggested that if stars could form with masses of 200-300 solar masses, there was no obvious upper limit to prevent even more massive objects from existing. Somewhere in the universe, there might be stars containing 500, 1,000, or even more solar masses, objects so massive they would blur the boundary between stellar physics and black hole formation. These theoretical super-hypergiants would burn through their nuclear fuel so rapidly that they might explode as pair instability supernovae, stellar deaths so violent they would completely destroy the star, leaving behind no compact remnant. Such explosions would be visible across billions of light years, briefly outshining entire galaxies. The fact that such events had not been observed suggested either that super-hypergiants were extremely rare, or that they existed in environments so distant or obscured that their death throes had not yet been detected. R136A1 had evolved from an anomaly into a window onto physics that operated at the very edge of what matter could achieve under the influence of gravity, nuclear forces, and electromagnetic radiation. Its existence suggested that the universe was far stranger, far more violent, and far more capable of surprise than even the most imaginative theoretical physicists had dared to propose. Confronted with observational evidence that challenged nearly a century of established stellar theory, astrophysicists around the world began constructing new theoretical frameworks that could accommodate the impossible existence of hypergiants like R136A1. Each proposed explanation required revolutionary modifications to fundamental understanding of how stars form, evolve, and maintain stability against the violent forces that govern their nuclear hearts. The leading hypothesis emerged from the chaotic gravitational environment of dense stellar clusters themselves. Dr. Simon Portuguese Zwart of Leiden University developed sophisticated computer simulations that modeled the gravitational interactions within clusters like R136. His work revealed that in environments with stellar densities thousands of times greater than typical galactic regions, direct stellar collisions and mergers could occur with surprising frequency. In Portuguese Zwart's scenario, R136A1 represented not a star that had formed with impossible mass, but rather the result of multiple stellar mergers within the cluster's gravitational cauldron. Several massive stars, each perhaps 50 to 80 solar masses and already pushing the conventional limits of stellar formation, could have combined through direct collisions or gravitational capture events. The resulting merged object would temporarily possess characteristics of its constituent components while gradually settling into a stable configuration. This merger hypothesis offered elegant explanations for several of R136A1's anomalous properties. The star's unusually rapid rotation, detected through careful analysis of its spectral line profiles, suggested it had retained angular momentum from multiple merging objects. Chemical abundance patterns in its atmosphere showed subtle variations that might represent incompletely mixed material from different stellar progenitors. Even its extreme mass could be explained as the sum of several smaller hypergiants that had combined through gravitational dynamics. Yet the merger scenario created its own theoretical challenges. Stellar collision events should produce highly unstable objects that would either explode immediately or shed their excess mass through violent stellar winds. Computer simulations of stellar mergers consistently predicted that merged objects should undergo rapid evolution, either fragmenting back into multiple stars or evolving quickly toward supernova explosions. R136A1 showed no signs of such instability, burning steadily with spectral characteristics indistinguishable from those of a single massive star. Alternative theories focused on the unique conditions present during stellar formation in the early universe. Dr. Volker Braun of the University of Texas at Austin proposed that hypergiants, like R136A1, might represent fossils of primordial stellar formation processes that operated under dramatically different physical conditions. In the early universe, gas clouds contained virtually no elements heavier than helium, conditions that would fundamentally alter the physics of gravitational collapse. Heavy elements normally serve as coolants during star formation, radiating away thermal energy and allowing gas clouds to contract efficiently. Without these cooling mechanisms, primordial gas clouds would remain much hotter during collapse, potentially allowing much larger masses to accumulate before nuclear fusion began, and radiation pressure could halt further contraction. Brahms' models suggested that the first generation of stars could have routinely exceeded 200-300 solar masses, creating a population of hypergiants that had never been directly observed, but whose descendants might persist in regions like the R136 cluster. The most radical theoretical framework came from Harvard University's Dr. Abraham Loeb, who proposed that hypergiant formation might require the influence of dark matter, the mysterious substance that comprises approximately 85% of all matter in the universe, but interacts only through gravitational force. Loeb's calculations suggested that in regions of exceptionally high dark matter density, the additional gravitational binding energy could allow stellar cores to remain stable at masses that would otherwise exceed the Eddington limit. In this dark matter scenario, hypergiants would represent visible markers of invisible cosmic structures. They could form only in locations where dark matter had concentrated to densities far above the cosmic average, creating gravitational wells deep enough to overcome the radiation pressure that normally limits stellar masses. The theory predicted that hypergiants should be found preferentially in galaxy centers, where dark matter densities reach their highest values, a prediction that seemed consistent with the location of R136 near the center of the Large Magellanic Cloud's most active star-forming region. Even more speculative theories explored whether hypergiants might require modifications to Einstein's general theory of relativity itself. Some theoretical physicists suggested that gravitational effects might become stronger than predicted under certain extreme conditions, allowing gravity to overcome radiation pressure more effectively than standard relativity would predict. Others investigated whether quantum effects during stellar core formation could create previously unknown states of matter capable of supporting much larger stellar masses. Each theoretical framework carried profound implications that extended far beyond stellar physics. If stellar mergers could create stable hypergiants, then dense stellar clusters should be cosmic factories producing objects that pushed the boundaries of what matter could achieve. If primordial formation processes could create 300 solar mass stars, then the early universe would have been illuminated by objects more luminous than entire present-day galaxies. If dark matter interactions influenced stellar formation, then the distribution of hypergiants could provide new tools for mapping the invisible architecture of cosmic structure. The theories represented more than academic exercises. They were attempts to understand whether R136A1 revealed new physics operating at the intersection of gravity, nuclear forces, and the fundamental structure of space-time itself. The enigma of hypergiant stars has mobilized the most sophisticated astronomical infrastructure ever assembled, creating an international effort that spans continents and extends beyond Earth's atmosphere into the depths of space itself. The James Webb Space Telescope, humanity's most powerful space observatory, has dedicated hundreds of hours of precious observing time to studying the Tarantula Nebula and its population of impossible stars. Webb's unprecedented infrared sensitivity allows it to peer through the cosmic dust that shrouds star-forming regions, revealing the thermal signatures of hypergiants with detail that was unimaginable just decades ago. From its position at the Lagrange point 1.5 million kilometers from Earth, Webb's instruments can detect individual stellar wind structures around hypergiants, mapping the complex patterns of mass ejection that carry away the equivalent of planetary masses every few millennia. The telescope's spectroscopic capabilities can measure chemical abundances in stellar atmospheres with precision sufficient to detect the subtle signatures that might distinguish between stars formed through conventional processes and those created through stellar mergers or other exotic mechanisms. On Earth's surface, a new generation of extremely large telescopes is under construction, specifically to address questions raised by R136A1 and its companions. The extremely large telescope, nearing completion in Chile's Atacama Desert, will possess a primary mirror 39 meters in diameter, larger than a football field, and capable of collecting 13 times more light than any existing optical telescope. When operational, the ELT will achieve resolution sharp enough to directly image the surfaces of nearby hypergiants, potentially revealing whether these stars show signs of rotation patterns, surface features, or atmospheric dynamics that could distinguish between formation scenarios. The telescope's advanced adaptive optics system will compensate for atmospheric turbulence with precision measured in nanometers, effectively creating a ground-based observatory with capabilities approaching those of space telescopes. Multiple instruments operating simultaneously across different wavelengths will provide real-time monitoring of hypergiant properties, tracking changes in stellar winds, surface temperatures, and mass loss rates over periods of years rather than decades. Equally crucial to understanding hypergiants is the revolution occurring in computational astrophysics. Supercomputing centers around the world run three-dimensional hydrodynamic simulations that model stellar formation and evolution in dense clusters with unprecedented detail. These simulations incorporate complex physics, including magnetohydrodynamics, radiation transport, stellar nucleosynthesis, and general relativistic effects. The calculations require months of computing time on machines capable of performing quadrillions of calculations per second. At the Max Planck Institute for Astrophysics, researchers run simulations that model the entire evolution of stellar clusters, like R136 from their formation in primordial gas clouds through millions of years of stellar evolution. The simulations track thousands of individual stars as they interact gravitationally, collide, merge, and evolve, testing whether the observed population of hypergiants can be reproduced through known physical processes or whether new physics must be invoked. Similar computational efforts at institutions like the University of California's National Center for Supercomputing Applications explore the role of dark matter in stellar formation. These simulations model the collapse of gas clouds in regions of varying dark matter density, investigating whether the additional gravitational binding energy provided by dark matter particles could enable the formation of stable hypergiants exceeding conventional mass limits. Perhaps most intriguingly, the future detection of gravitational waves from hypergiant stellar collapse could provide definitive tests of competing theories about these objects' nature. When stars as massive as R136A1 eventually exhaust their nuclear fuel, they should collapse to form black holes through processes that generate gravitational wave signals, unlike anything previously observed. The proposed Laser Interferometer Space Antenna mission, planned for launch in the 2030s, would be sensitive enough to detect these signals from hypergiants throughout the observable universe. LISA's measurements could reveal whether hypergiants collapse to form single massive black holes, as expected for stars formed through conventional processes, or multiple black holes, as might be expected if hypergiants represent merged stellar systems. The gravitational wave signatures could also provide direct measurements of hypergiant masses independent of optical observations, potentially resolving debates about whether these objects truly exceed theoretical mass limits or whether systematic errors in spectroscopic analysis have led to overestimates of the properties. Ground-based gravitational wave detectors like LIGO and Virgo are being upgraded with enhanced sensitivity that could detect hypergiant collapse events in nearby galaxies, while next-generation facilities like the Einstein telescope will push detection capabilities to cosmic distances that encompass the epoch when hypergiants might have been more common throughout the universe. Spectroscopic surveys using facilities like the Very Large Telescope are systematically searching for hypergiant populations in distant galaxies, attempting to determine whether R136A1 represents a rare anomaly confined to unusual environments like the Tarantula Nebula, or evidence of a previously unknown stellar population that was more abundant in the universe's violent youth. In the end, R136A1 forces humanity to confront a profound and humbling truth. The universe still harbors secrets that dwarf our understanding, mysteries that render our most sophisticated theories incomplete. This single star, burning with the luminosity of entire galaxies, yet concentrated into a sphere that could fit within the orbit of Neptune, stands as a monument to the limitations of human knowledge and the endless capacity of the cosmos to surprise us. The existence of hypergiants suggests that the universe operates according to principles far more complex and subtle than our current physics can fully describe. For nearly a century, the Eddington limit stood as an immutable law, a fundamental boundary that defined what was possible in stellar physics. R136A1 shattered that boundary with casual indifference, burning peacefully in defiance of theoretical predictions, while challenging every assumption about how matter behaves under the most extreme conditions nature can create. Perhaps what is most profound about this cosmic riddle is not simply that it reveals gaps in our scientific understanding, but that it illuminates the deeply human tendency to mistake our current knowledge for complete knowledge. The discovery of hypergiants reminds us that science is not a collection of finished truths, but an ongoing dialogue between human curiosity and cosmic mystery, a conversation in which the universe consistently proves more imaginative than its would-be interpreters. The implications extend far beyond stellar physics into the deepest questions about the nature of reality itself. If stars can exceed their theoretical limits through mechanisms we have yet to understand, what other fundamental assumptions about the universe might be incomplete? What other impossible objects might exist in the depths of space, waiting to shatter our theoretical frameworks once again? The cosmos that contains R136A1 is not the orderly, predictable universe that classical physics once promised us, but something far stranger and more magnificent. These stellar monsters may represent windows into the universe's most violent epoch, the cosmic dawn when the first stars ignited in the primordial darkness following the Big Bang. If hypergiants were more common in the early universe, as theoretical models now suggest, then the cosmos was once illuminated by objects more luminous than entire present-day galaxies. These primordial giants would have lived fast and died young, exploding as supernovae so violent they could be seen across billions of light-years, enriching the early universe with heavy elements at rates that fundamentally shaped the evolution of galaxies, planets, and ultimately life itself. The story of R136A1 is ultimately a story about the relationship between knowledge and wonder, between scientific achievement and intellectual humility. As our instruments become more sophisticated and our theoretical frameworks more comprehensive, we might expect the universe to become more predictable, more completely understood. Instead, each advance in observational capability seems to reveal new layers of mystery, new phenomena that challenge our most fundamental assumptions about how reality operates at its extremes. R136A1 burns on in the Tarantula Nebula, a cosmic lighthouse that illuminates not just the space around it, but the vast darkness of our own ignorance. Its impossible light carries a message across 13 billion years and 160,000 light-years of space, a reminder that we live in a universe far stranger, more beautiful, and more terrifying than we have yet learned to imagine. In its blue-white radiance, we glimpse both the hidden violence that shapes cosmic structure and our own endless capacity for wonder in the face of the unknown. As we continue to study this impossible star and its companions, we are not merely learning about stellar physics or galaxy formation. We are engaged in something far more profound, a confrontation with the fundamental mystery of existence itself. Why does the universe seem designed to exceed our attempts to comprehend it? Why does reality consistently prove more complex and magnificent than our theories predict? Why do we live in a cosmos where stars can burn brighter than galaxies and matter can achieve configurations that should be impossible? These questions may have no final answers, and perhaps that is the most beautiful truth of all. R136A1 reminds us that the universe is not a puzzle to be solved, but an infinite source of wonder to be explored. Each answer we discover reveals 10 new questions. Each boundary we map dissolves to reveal territories we never suspected existed. In the impossible light of the hypergiant, we see reflected both the limits of human understanding and the limitless capacity of the cosmos to inspire awe, humility, and an endless desire to know more about the magnificent mystery in which we find ourselves embedded. The star that outshines galaxies burns as a beacon of everything we do not yet know, everything we may never fully understand, and everything that makes the universe endlessly worthy of our wonder and our quest to comprehend our place within its vast, impossible beauty.